Okay, welcome to AI Paper Podcasts. Today, we're diving into a paper that's maybe pushing back a bit on the recent dominance of diffusion models in image generation.
Yeah, it's looking at the classic autoregressive approach and saying, hey, maybe we don't need all the complexity.
Exactly. It's all about simplicity here. They took a standard, or vanilla as they call it, autoregressive framework, and seem to have gotten some pretty impressive results through really smart training and optimization.
Right. The paper is SimpleAR, pushing the frontier of autoregressive visual generation through pre-training, SFT, and RL.
And our job today is to unpack what SimpleAR is doing, why it's working so well, and what it might mean for you if you're working in this space, maybe as an AI researcher or an ML engineer.
Sounds good. And for anyone needing the super quick version, we've got that lined up first.
For short form, edit first minute summary start. All right, headline. SimpleAR, high-resolution autoregressive image generation made simple and fast.
Key insight 1. SimpleAR uses just 0.5 billion parameters. Pretty small these days in a straightforward autoregressive model. But it generates high-quality 124 by 124 images.
And gets really competitive scores, right?
Yeah.
Like 0.59 on Geneval and 79.66 on DPG.
Exactly. It's actually outperforming some bigger diffusion models on those benchmarks, which is quite something for parameter efficiency.
Key insight 2. The magic isn't fancy architecture, it's this 3-stage training pipeline. They start big with pre-training, then refine with supervised fine-tuning, or SFT, using high-quality data.
And then the crucial third stage, reinforcement learning, RL, using something called GRPO. They found using a CLIP reward there really pushed the image quality and how well it followed the text prompt.
And key insight 3, which is maybe the most practical bit, they tackled the speed problem. Autoregressive models are usually slow.
Yeah, but they use optimizations from large language models, things like KV cache and vLLM. You got the generation time for a big 1024 by 1024 image down to about 14 seconds. Makes it actually usable.
For short form, edit, first minute summary end. Okay, stick around as we get into the details of how they did all that. So let's start with that core idea, vanilla autoregressive. What does that really mean for generating an image? Why go simple?
Well, vanilla here just means sticking to the basics of autoregressive generation. You treat the image like a sequence of visual tokens.
Okay.
And the model predicts the next token in the sequence based on all the ones that came before it. Just like an LLM predicts the next word. They didn't add complex stuff like UNets or special attention mechanisms you often see in diffusion models.
Right. So keeping the core mechanism simple, how does that simple model handle both the text prompt and the image generation together?
So that's the architecture part. They use a visual tokenizer, specifically one called Cosmos Tokenizer here, to turn the image into that sequence of discrete codes, or tokens. It has a vocabulary of 64,000 possible tokens.
So it breaks the image down into pieces represented by these tokens.
Exactly. It downsamples the image by 16 times in this case. Yeah. And then, of course, you have a standard text tokenizer for the input prompt.
Okay, got it. Image tokens, text tokens.
And here's the key unification part. Unlike some diffusion setups where a text encoder feeds information into the image generation process separately,
Yeah.
SimpleAR puts both the text tokens and the visual tokens into one single decoder-only transformer.
Oh, interesting. So it's just one long sequence for the transformer. Prompt first, then the image token.
Pretty much, yeah. The visual tokens are usually flattened out, like reading a page row by row, left to right. This combined sequence goes in, and the transformer just learns to predict the next visual token using everything it's seen so far, the text and the image parts already generated.
That makes sense.
What's
A
that?
unified way to handle both modalities.
And they argue this helps with multimodal alignment, getting the text and image parts to really understand each other.
Okay, simple architecture, unified model. But you mentioned the training was where the real cleverness comes in, that 3-stage pipeline.
Yes, exactly. Stage 1 is large-scale pre-training. This is about learning the fundamentals.
And they threw a lot of data at it, right? CC3M, CC12M, open images, SAM1B, looks like around 43 million images.
Yeah, pretty broad data set mix. They did this pre-training at 512 by 512 resolution. The goal here is just general pattern recognition, learning what images look like, basic text-image connections.
And the objective is just predicting the next visual token.
Yep, standard language modeling loss, but predicting visual tokens based on the text and the previous visual tokens. And that same loss carries over to stage 2, Supervised Fine-Tuning, or SFT.
Okay, so what changes in SFT?
Higher quality data and higher resolution. They use data sets like JourneyDB, a synthetic data set, and some internal data. Crucially, they curated it carefully.
How so?
They filtered for images that were at least 124 pixels on the short edge And they actually recaption a lot of it using a powerful vision language model, Qwen2VL, to get really good descriptive text prompts.
Ah, okay. So better data, better prompts, and now training at the target 1024 by 124 resolution. This sounds like it's focused on quality and instruction following.
That's exactly the idea, sharpening the model's abilities. And then you have stage 3, reinforcement learning with GRPO.
RL for images still feels a bit novel. Why bring in RL here? What's GRPO doing?
It's a good question. RL is often used to fine-tune models based on reward signals that better capture what you actually want, like aesthetic quality or precise alignment with a complex prompt, which might be hard to capture perfectly with just the SFT loss.
And it helps with that exposure biases problem too, right?
Right. Exposure bias is where, during training, the model always sees the correct previous tokens, but at inference, it has to generate based on its own previous tokens, which might contain errors. RL can help make the model more robust to its own predictions.
Makes sense.
In GRPO, Group Relative Policy Optimization is just an RL algorithm that's known to be pretty stable and efficient for these big sequence models. It optimizes the main model against a frozen copy from the SFT stage, trying to maximize a reward score while staying reasonably close to what it learned during SFT.
What rewards did they use to guide it?
They tried a couple, including CLIP and HPSV2. They reported that the CLIP reward, specifically CLPVITH14, gave the biggest improvements.
How big?
For the 0.5 billion parameter model, it boosted the Genival score by 0.6 points, which is pretty significant for just one stage of tuning.
Wow, yeah, that's a noticeable jump. Did they show visually what kind of improvements that CLIP reward brought?
They did. They had examples like generating text inside images. Think of a stop sign. Before RL, the text might be garbled. After RL, with the CLIP reward, it was rendered correctly.
Ah, because CLIP is good at judging text-image similarity.
Exactly. It helped with things like getting quantities right, 2 apples versus just apples, and understanding spatial descriptions in the prompt better. They actually showed a nice plot correlating the CLIP reward score during training with the final Genival performance, suggesting it was effectively steering the model in the right direction.
Okay, so simple structure, but this sophisticated 3-stage training with RL at the end. How does it actually perform against the competition? What do the benchmarks say?
If you look at Table 1 in the paper, it's pretty clear. Comparing their 0.5b model to others under 1 billion parameters, especially diffusion models like Stable Diffusion 1.5 or 2.1.
Which are around 0.9 billion parameters, plus a text encoder usually.
Right. SimpleAR comes out ahead on both Genival and DPG benchmarks. SimpleAR gets 0.59 Genival and 79.66 DPG, while SD 1.5 is like 0.38 and 74.63, and SD 2.1 is 0.51 and 68.09.
That's quite a lead, especially considering the potential parameter efficiency advantage from that unified transformer.
It really seems to be efficient. And they also show it scales well. They trained a 1.5 billion parameter version, and the scores went up consistently, 0.63 Genival, 81.97 to DPG. It scales predictably, kind of like we see with large language models.
Though they are upfront that it doesn't quite match the very biggest models out there, like DELI 3 or others, on every single metric yet.
True. They're very competitive for their size. But reaching the absolute state of the art might need even more data, or maybe improvements in that visual tokenization step, which they mentioned as an area for future work.
Let's touch on the Ablation Studies quickly. They tried initializing the transformer with LLM weights. Did that help?
Surprisingly, not really, according to their Table 2 results on DPG Bench.
Why not?
The paper suggests maybe the benchmark prompts were too simple to benefit, or perhaps the intense image text training caused the model to sort of forget some of the language nuances it might have had from the LLM initialization. It kind of highlights that you really need good text data during the visual training.
It's interesting. And what about using 1D versus 2D positional encodings for the image tokens? 1D feels weird for an image.
Yeah, you'd think 2D might be better for spatial awareness. Right. But in their tests, again shown in Table 3, the standard 1D positional encoding actually did slightly better during pre-training on DPG Bench. They do note, though, that for things like handling different image sizes dynamically, or especially for moving to video, 2D encodings would probably be necessary.
Okay, that makes sense. But let's get to the elephant in the room for autoregressive models. Speed! Generating token by token sounds painfully slow for a high-res image.
It traditionally is, yeah. And this is where I think SimpleAR makes a really practical contribution. They basically said, hey, LLMs generate token by token too, and people have made them fast. Let's use those tricks.
Borrowing from the LLM serving playbook, things like KV cache and vLLM, could you briefly explain what those are for folks maybe less familiar with LLM inference?
Sure. So KV cache, key value cache, is fundamental. When a transformer calculates attention, it computes key and value pairs for each token. To generate the next token, it needs to look back at all previous tokens.
Right.
Without KV cache, it recalculates these keys and values for the whole sequence every single time, which gets slower and slower. KV cache just stores these keys and values, so for the next step, you only compute them for the newest token and reuse the rest. Huge speed up.
Okay, avoids recomputing everything constantly. And vLLM.
vLLM is a specialized library or serving engine for running LLMs efficiently. It has clever ways to manage that KV cache memory, especially when handling many requests at once, using techniques like page attention. Applying it here means using those highly optimized LLM tools for the visual sequence generation in SimpleAR.
And the impact was significant.
Oh yeah. Table 5 shows it starkly. The baseline inference for one 124 by 124 image took over 227 seconds. Just adding the KV cache optimization brought it down to around 150 seconds, already a decent improvement.
Still pretty slow, though.
But then, using vLLM, they got it down to 13.55 seconds per image.
Wow. Okay, that's night and day. That actually makes it practical.
That's a massive difference. Suddenly, high-res autoregressive generation isn't just a research curiosity.
They also explored something called Speculative Decoding, SJD. What was that about?
Right, SJD is another optimization idea. You use a smaller, faster draft model to predict a chunk of tokens ahead. Then the main, larger SimpleAR model checks these predictions in parallel.
So if the draft model guesses right, the main model can accept multiple tokens at once.
Exactly. It lets you potentially skip generation steps. And Table 6 shows it did significantly reduce the number of steps, like from over 4,000 down to about 2,000 in one configuration.
Did it reduce the actual time, though?
Interestingly, not in their reported setup. While it cut steps, the way they implemented the verification still took about the same wall clock time per image. But it did slightly improve the DPG scores, maybe by exploring slightly different generation paths. So it's still a promising technique, perhaps needing more implementation work for latency gains.
Looking at the actual images they produce, figures 1, 4, 5 in the paper, the quality seems really good for a 0.5B model. That cat playing chess, the detailed portraits.
Yeah, the fidelity is impressive. And figure 5, showing the before and after RL examples, like those stop signs of the apples becoming much more defined, really drives home the impact of that final tuning stage. The instruction following shown in figures 4 and 5 on benchmark prompts the pizza, the 2 beds, the cat wizard looks pretty solid too.
But they were also good about showing failures in figure 6. Where does SimpleAR still struggle?
Common areas, really. Complex human poses, like a dancer, could be awkward. Accurately generating a specific number of distinct objects, like 2 bears, sometimes failed. Coherent text generation within the image is still hard, which isn't unique to SimpleAR.
Yeah, text is tough for most models.
And physics-defying scenes or really complex compositions could also cause problems. You know, apples taking a shower, that kind of thing.
And they put these down mostly to the current scale of data and parameters.
That seems to be their main hypothesis. They suggest that scaling up both would likely mitigate many of these issues, mirroring the trends we've seen in LLMs.
Okay, so pulling it all together, SimpleAR seems to demonstrate quite powerfully that simple autoregressive architecture can be really competitive for high-res image generation.
Yeah, if you combine it with a smart, multi-stage training process that pre-training, SFT, and especially the RL refinement, and crucially, leverage modern inference optimizations from the LLM world.
It definitely puts AR models back on the map as a potentially efficient and high-performing alternative to diffusion models, maybe challenging the idea that you need extreme architectural complexity.
Exactly, and they pointed to clear next steps too. Improving the visual tokenizer is one they admit the current one might limit fine detail.
Right. Faces, small text, things like that.
Text to video is the obvious but much harder next frontier for sequential generation.
Of course.
And ultimately, it's all moving towards these native multimodal models that handle everything, text, vision, maybe audio in one unified system, which SimpleAR's architecture kind of leans towards.
Well, that was a really insightful look at SimpleAR. For anyone listening who's working in AI research or engineering, I think this paper offers some really concrete ideas about effective training strategies for AR models and shows just how much performance, especially speed, can be unlocked with existing optimization techniques.
It definitely makes you pause and think about whether the answer is always more complex architectures or sometimes just better optimization of simpler ones.
So here's something to think about. Given that SimpleAR got so far with a relatively straightforward autoregressive setup, mostly through clever training and applying LLM speed tricks, what does this really suggest about the fundamental ceiling for AR models versus diffusion? Could we see a future where highly optimized, scaled-up AR models actually become the preferred approach for generation, maybe even surpassing diffusion in some areas? Definitely food for thought.